Okay, guys, so today we're going to talk about equations and pH of strong and weak bases. So yesterday we talked about acids, strong and weak acids, and now we're going to talk about the bases. Okay, so the definition of a base, of course, is a substance that increases the hydroxide concentration. Okay, so one second. Okay, so pH is always higher than 7. The hydroxide concentration is always greater than the hydronium concentration. And in an acid base, you always have hydroxide as the product and a conjugate acid. Okay, so this is going to be important when we write the equations. Okay, when we wrote the acid equations, we always had hydronium as a product and a conjugate as well. Okay, there are two ways that hydroxide ion can increase. Number one, the substance, okay, the compound that you start with in the reactant side has an anion, which is the OH, and it dissociates to release OH. Okay, this is the Arrhenius definition. Okay, the Arrhenius definition says if it is a base, when you put it in water, it will make OH ions. That's the Arrhenius definition. Okay, or number two is from the Bronsted-Lowry definition of a base, where it is a substance that accepts a proton from water, leaving OH. These Bronsted-Lowry bases have no hydroxide in the formula. Okay, so instead, your clue is that it's going to end in N, NH, or NH2. So here's some examples of some Bronsted-Lowry bases. Things that can take H plus from water. Okay, so there's two types of bases. Your Arrhenius bases that already have OH in them, okay, and dissociate to form OH, or your Bronsted-Lowry bases that accept a proton from water, leaving OH. Okay, but let's first talk about strong bases and how to tell it's a strong basis. With the acids, I gave you 6 of them to memorize. Okay, here you do not have to memorize them, but it's the same definition. They go to completion. There's no equilibrium value, or there's no equilibrium. It's a strict left to right completion reaction, no K value, just like the strong acids. They are literally just dissociation equations. The strong base breaking up into 100% ions. When you write it, you do not write it with water. Okay, so that's an important point when you're writing the equation for a strong base. You do not put water in the equation. So for example, if you were writing, well, we'll do it in a minute. We have some examples here. Okay, so what are the strong bases? Group 1 and group 2 soluble hydroxides. Okay, so group 1 would be lithium hydroxide, sodium hydroxide, potassium hydroxide. Okay, barium hydroxide, strontium hydroxide, these are all group 1 and group 2 soluble hydroxides. Things like iron hydroxide, copper hydroxide, they would not be strong bases. Okay, and this is something we learned in honors. Okay, so if I was going to write the strong base reaction, notice it's a completion reaction, it's just dissociation. You don't write water in it, and you're just dissociating it into its 2 ions. Okay, potassium OH. Okay, so that would be the dissociation reaction for 2 strong bases. Okay, now, to figure out the pH of a strong base, okay, you're going to use what you know from Unit 3A and ion molarity to determine the OH, okay? What that means is your mole ratio. You got to know how many moles of OH you have for every mole of compound. Okay, let me pull out my notes here. Let me pause this. All right. Okay, so let's look at this first one here. Okay, so when we calculated the pH of the strong acids, we used our pH formula, right? Which is the negative log of the hydronium ion. Okay, but in this case, remember, if we want pH, we're going to actually use two equations. We have to start with the POH and then get to pH by using our second equation. And that should be something you remember from honors, but if not, we're doing it right now. Okay, so if you look at this, you got to recognize, yeah, you have 0.25 moles per liter of the strontium hydroxide, but you want, for your equation, you just need hydroxide. Okay, you've got 2 moles of hydroxide for every mole of compound. Okay, so let me just show you the mole relationship. And if you don't want to write it out every time, I don't think you have to. Okay, but remember, you got 2.25 moles of compound. I'm just going to write compound instead of strontium hydroxide per liter. Okay, and you've got 1 mole of compound per 2 moles of hydroxide. 2 moles of hydroxide. Okay, which makes 0.5 moles of hydroxide. Okay, now you don't have to show this factor label at every time. You could just multiply by 2. But now when we get the POH, now we have the hydroxide concentration. So you could put negative log of 0.5, okay, and that equals 0.3. Okay, now I have to use that other equation. They didn't ask for POH, so I'm going to use pH equals 14 minus POH, this formula right here, which is 0.3, and I end up with 13.7 as my pH for this first one. Okay, so what I did was I made sure I knew the moles of hydroxide, okay, which was different than the moles of compound, or the moles per liter, excuse me, of hydroxide, the molarity. Okay, and then to get pH, I needed to subtract from 14. Okay, now let's look at this next one. Now this next one, you can see you have a 1-to-1 ratio, so I really don't have to do anything. It's a lot easier. So I'm going to get the POH is the negative log of 0.25, and I get 0.6, and then pH is 14 minus 0.6, which is 13.4. I should have had you guys do this one yourselves. Okay, so strong acids, strong bases. Like I said, no ice table. And you can just use your honors, pH, POH. 14 equals POH plus pH formulas. All right, I'm going to keep it moving since I know what it looks like when I watch my own video. All right, now here's the part where you are going to start needing your ice table. Okay, this is where you're going to write your equation and write your KB, which is what we're going to talk about. Okay, weak base equations, these are more like the Bronsted-Lowry, right? Remember that the acid equals the proton donor. It gives it away, and the base is the proton acceptor. Okay, it's going to take a proton, and it's going to take it from water. Okay, so you watch the direction the H moves. It's opposite than with the acids. Acids, H plus goes to the water. In weak bases, the H goes away from the water, right? It's accepting the H from the water to form this equilibria. So here's a really common weak base. This is ammonia, which is NH3. Okay, so when you write the equilibrium equation, you have water in it, okay? So notice that, which is very similar to the acid equation. Now, remember the base is going to be the proton acceptor. Okay, so that means it's going to take that H, it's going to become NH4 plus, it takes the proton, and now the H2O lost the H, so it becomes OH minus. Okay, now if we look at this one here, same idea. Base is going to be the proton acceptor, so it's going to be C2H5 and H3. And of course the water lost that proton, so it's becoming OH. You You see these are both in equilibrium. Okay. Now, weak bases need Kb values. Okay, so we looked at the Ka values, but there's a Kb value. You're going to create an equilibrium, and you need a Keq value, now called Kb. Okay, so with a base, weak bases, we now have a Kb. The larger the Kb, the stronger the base. The more hydroxide, the higher the pH. Okay, so as Kb goes up, the OH goes up, and of course the pH goes up. Okay, now here's some Kb values. Okay, you can see ammonia at the top. Okay, Kb of 1.8 times 10 to the negative fifth. Okay, so that is the strongest of the weak bases. Okay, so strongest up top, weakest down here. Okay, this is obviously a table you would need to look up, not memorize. Okay, so let's do a little problem. Let's take this and we'll compare. Okay, so why don't we see if you can do this. Okay, answer these problems now. Okay, we'll do the first one together, and then I want you to answer the second one, or we'll do the third one yourself. Okay, so which is the stronger base, NH3 or C6H5NH2, which happens to be aniline. Okay, let's circle them in green or red. I'm colorblind today. Okay, so the Kb for ammonia is 1.8 times 10 to the negative fifth. The Kb for aniline has a negative 10th. It's a lower number. So our stronger base would be ammonia. Okay, the stronger the base, the more what is present in solution? Anybody want to shout out or put in the chat? What would be present in solution in a higher quantity for a stronger the base? Good, OH. Okay, so this would be hydroxide or OH, -1 ion, which would have a higher pH given equal molar solutions. Notice they have to say equimolar because you could have a very concentrated solution making it a higher pH. Okay, so let's see, we've got the C2H5NH2, which is right here. The second one, and then we have the CH3, C2, I circled the second one, and then the third one is C2H5NH2, it's right below it, okay. So the CH3 would have the higher value. Okay, so that's how you read a Kb table. All right, now we're going to do some problems together. We don't have too many, okay, but we do have a thinker problem too that we'll do. Okay, so with the pH of a weak base, just like the weak acid, you need the ICE table. You need the law of mass action, and you write the Kb value. Okay, so when you start going into these problems, write that equation right away. Set up the ICE table and write what the Kb expression should be to get you started. Okay, so let's move this up a little bit. And let's solve this problem. Okay, so we have a 0.25 molar solution of C2H5NH2. The first thing I'm going to do, the very first thing, is write my equation out. Okay, so I have C2H5NH2. Now I recognize that's a base. It's going to be a weak base. Okay, I'm going to react it with water. Okay, and then it's going to accept a proton. So we're going to get, our product is going to be C2H5 NH3 plus. Okay, and then the water is going to lose a proton, so it's going to become OH minus. Okay. Okay, so remember this is aqueous. This is liquid. Aqueous. Aqueous. Okay. Now what I could do too is I can set up my KB expression too. So let me do that. I'll just do that down here so I have some room. KB is going to be equal to the products, just the same formula as K. It doesn't matter which K it is. KB is going to be the same. So it's going to be C2. This thing is really struggling today. C2, H5, and H3 plus times OH negative over, and remember you don't include water in the expression, C2H5 and H2. Okay, there's my KB expression. Will I need it? Not sure. We'll see. Okay, all right, so now I did look this up from the table, okay, and my KB is 5.6 times 10 to the negative fourth, so I looked it up on the table. So this is from the table. Okay, so that's the KB of this. Okay, so this is from the table. Okay, so let's write our ICE table. So ICE. Okay. The initial amount of the base is 0.25. That's given in the problem right here. Okay, we don't do 0, so I'm just going to cross out the whole thing. And we start out with 0 products. Okay, the change is according to the stoichiometry. So this is going to be a minus x, this will be a plus x, and this will be a plus x. So we have 0.25 minus x, I plus c. Excuse me, I think I said plus x. 2.25 minus x, and x. Okay, now we want to know the pH. Okay, well, to get the pH, the key to getting that is to get this hydroxide concentration. We need to know what X is. And since we don't have any other givens, we're going to have to use the KB expression to solve for X. Now, we talked about this yesterday, but remember when the KB is less than 1 times 10 to the negative fourth, we can eliminate the X in this equation on the reactant side because it's negligible. Okay, so if it's less than 1 times 10 to the negative fourth, we can eliminate that because it's negligible. You can even see when we plug it back in how negligible it is compared to the 0.25. Okay, so we're going to cut that out. Okay, so now I'm going to write the KB expression. Actually, what I'm going to do is move this down so we have some space. Okay. Okay, so now I'm going to write the KB expression with, let me just erase this. I don't know what happened here. Okay, forget it. Forget it. All right, KB, I'm just going to write it with the X's. I'm plugging the X's for the expressions up here. So KB is X squared, X times X over 0.25, which equals 5.6 times 10 to the negative fourth. That's from the table. Okay, so I'm going to take that 5.6 times 10 to the negative fourth, multiply by 2.5, take the square root of the whole thing, solve for x, and I get x equals 0.012. Okay, see how small x is? Okay, so x is 0.012. Okay, now I want pH, but the only thing I can get from x is the pOH, because this is the x right here. Okay, so first I'm going to get pOH, which equals negative log of 0.012. And I get my pOH as 1.9. Now to get pH, I'm going to use my second formula, which is pH equals 14 minus 1.9. And I get 12.1. Okay, so that is the answer to the first part of this question. pH is 12.1. Okay, so what I've done is I wrote the equation, I wrote my equilibrium expression, I did my ice table, solved for my concentration of hydroxide, got my pOH, got my pH, and now the last thing they ask us is the percent ionization. Okay, well this formula, remember, is something you need to remember. Okay, percent ionization or dissociation. It's the same formula as we learned yesterday. It's going to be the x, which is the change from the ice table, over the initial amount. In this case, it'll be the initial amount of the base. Yesterday, we used the acid. Okay, and then, of course, it's times 100. So that's going to be, x is going to be 0.012. I is 0.25. It's given in the problem. Okay, just to make sure you understand where this I came from, it's right here. Okay, and the x is right here. Okay, times it by 100. And I ended up with 4.8%. Okay, so you always remember that percent dissociation or ionization is x over I, change over the initial amount times 100. Okay, this last one is a thinker problem. Okay, so let's see if I'm going to give you about, let me give you about 10 minutes to see if you. Okay, so let's go through this. We have a solution of an unknown base, and it has a pH of 8.1 with a percent dissociation of 1.22. Write the equation in water, determine the molarity of the original solution, and the Kb value. Okay, so let's see how far you got. Okay, so the first thing I'm going to do is write the equation. Okay, so I have a base, B. Okay, and I'm reacting it with water. Okay, now remember the base is going to be a proton acceptor. Okay, so that's going to be BH plus OH. Okay, so the base accepted the proton, the water lost the proton. Okay, the next thing I'm going to do is I'll write down here, I'll write the equilibrium expression. So I've got Kb equals, okay, it's going to be BH plus times OH over B. Remember, water is not part of it. Okay. So I got my equilibrium expression. So I could write those two things. Hopefully you guys could too. And the last thing is to set up the ice table. Hopefully you're able to set up the ice table. Maybe not solve it, but set it up. Okay, so for the initial amount of the ice, we don't know the initial amount of B. That's actually what we're trying to solve. So what I'm going to do is I'm just going to make the variable, since I already used X, I'm going to make it I. Okay, so I'm going to call my new variable for the initial amount of B, I'm going to call it I. Okay, I hope that's okay. Okay, I don't need water here in this expression. I start out with 0 over here. Okay, my change will, of course, be minus x, x, and x. And then my e, which is my I plus my c, will be I minus x. So that would be I minus x. Sorry, it's kind of getting crowded here. This will be x, and this will be x. Okay, so my e is I minus x. Let me just circle that so you can see it and not get crowded. All right, so I got a lot of unknowns so far. Okay, a lot of unknowns so far. Okay, let's see what I need to solve this. Okay, well, let me also write down the formula for percent dissociation just to see what I know there. Okay, so percent ionization or dissociation is going to be x over I times 100. Okay, well, I don't know x, I don't know I, and I know 1.22. Okay, so again, I have two variables. All right, but I am given the pH of 8.1. Okay, now remember X over here is the concentration of hydroxide. So I can, if my pH is 8.1, okay, I can solve for my pOH, which is going to be 14 minus 8.1. And I can get my pOH as 5.9. Okay, now I can get the concentration from the pOH. 10 to the negative pOH, which is the inverse log, is equal to the concentration of OH. Okay, which equals 10 to the negative 5.9. When I do that, I get 1.3 times 10 to the negative 6. Okay, and that also equals x. So this is actually, this is 6 here. That's also my x value. Okay, so now I actually don't even need this KB equation because now I have my x value and I can actually solve for my I right here. Okay, so what I'm going to do is erase this KB equation because I didn't even need it. Let's just get rid of it to make some room here. Oh, I do, because they asked me to solve for 8 kV. Sorry, but we do need it, but we'll bring it back. It's not a big deal. Okay, so let's find the original x, or excuse me, I. So what we're going to do is rearrange this equation right here to solve for I. Okay, so when I arrange it to solve for I, oh no, crap. It's going to stop working. Oh, cross your fingers. Do we have sound? We'll see. All right, so what I'm going to do is rearrange this equation to solve for I. Okay, so what we get is I equals x over percent dissociation, or I, let me just make it the same variable, sorry, percent I. Times, okay, times 100. It's so funny. She's cute. All right, so let's finish this, sorry. Anyway, so it's x over percent I times 100. Okay, so all I did was rearrange this, our equation down here, okay? And when I do that, to save time, let's see, I plugged in the 1.3 times 10 to the negative 6. That was my x I just solved for. Okay, that was my x over here, which is right here. divided by percent I, which is 1.22. They gave us that in the problem. That's right here. They gave us that in the problem. Okay, times by 100. I know I'm running out of room. I'm going to come over here, and I end up with a I, which is the initial amount of, I end up with 1.1 times 10 to the negative fourth. 1.1 times 10 to the negative fourth. Okay, so that's what I get as my initial amount I. So that's how much I started with, which is the first part of the problem. Then they want the KB. Okay, I'm just going to go to another page because I'm running out of room. Remember the KB expression I had on there that I erased, but instead I'm going to plug in the actual values of x. So KB is going to be, remember, x squared over what I minus x. Okay, and I've got all the values now, so that's going to be 1.3 times 10 to the negative 6 squared. That's when I solve for x. I just got, which is 1.1 times 10 to the negative fourth minus the x, which is 1.3 times 10 to the negative 6. You can see how negligible that is, right? And I end up with a KB. I think I may have made a little, I may not have subtracted this one, so you may be a little off, but I got 1.5 times 10 to the negative 8 as my KB for this problem.